Hey, have you ever stopped to think about what's really happening when you click on an icon? Today, we're going to pull back the curtain and uncover the secret life of code. How a simple file on your computer wakes up and becomes a living, breathing action on your screen.
We all do it. We say we're running a program when we open an app. But what if I told you that's not exactly right? Yeah, it seems like a small thing, but this little mix-up hides one of the biggest, most important ideas in all of computing.
All right, here's the best way to think about it. Imagine a program is a recipe book sitting on your kitchen shelf. It's full of instructions, full of potential, right? But it's not actually doing anything, it's just sitting there. A process, though, that's you in the kitchen with that book open, actually mixing the flour, cracking the eggs. You're making the cake. A process is the recipe in action.
So, when you get right down to it, a program is really just a file. Like an exe file on Windows. It's just sitting there, quietly on your hard drive or your SSD, holding all the code and data needed to do something. Just waiting for its big moment.
But here's the thing. It can't just be a jumble of code. That file has to have a very specific format. It's a structure that basically tells the operating system, hey, my instructions, they start right here, and the data I need, that's over there. Without that format, the computer would be totally lost. It'd be like trying to bake a cake with all your ingredients just dumped on the counter with no labels. Good luck with that. And this is where the magic really happens. When you double-click that program file, the operating system steps in and creates a process. It takes that recipe book off the shelf and brings it to life. Suddenly, it's not just potential anymore. It's a living, running instance of that program, finally doing the job it was made for. So how does it keep its place? Well, every single process has this little thing called a program counter. And honestly, the best way to picture it is to think of your own finger pointing at the current step in the recipe as you're cooking. That's all it is. It tells the computer's brain, the CPU, exactly which instruction to do next, making sure everything happens in just the right order. Okay, so we know a program becomes a process, but that just kind of backs the question up a step, doesn't it? Where did that program file even come from? How do we get from code that a human can write to something a computer can actually understand and run?
It's basically a two-part journey. First step is compilation. This is where a cool program called a compiler takes the code that humans write, in languages like C or Java, and translates it into the raw ones and zeros, the machine code that the processor actually gets. But that's not the end of the story. The second step is linking. This is where all those different translated bits and pieces get assembled into one single, complete, runnable file.
You might be wondering, hold on, if compilation translates the code, why do we need that second linking step? And that's a great question. It's because modern software is, well, it's complicated. You're almost never working with just one file. You've got your own code, sure, but you're also using tons of pre-written code from libraries to do common stuff.
And that's where the linker comes in. It's kind of the unsung hero of this story. Think of it like a master puzzle builder. It takes your compiled code, it goes and finds all the library pieces you need, and it expertly snaps everything together to create that one final complete picture, the executable file.
And the linker has two main ways of doing this. First, there's static linking. This is like packing your entire lunch, the sandwich, the chips, the juice box, all into one giant container. It's got everything it needs, but man, it's heavy. Then there's dynamic linking. This is more like packing your sandwich and then putting a little note in your lunchbox that says, hey, when you're thirsty, the drinks are in the fridge. The file's way smaller, but it totally depends on the fridge being there when it needs it. This is super common because it saves a ton of space.
And that trade-off with dynamic linking, the small file size versus needing other files to be there, it's not just some theory. Oh no, I learned this one the hard way a long, long time ago with a silly mistake I made with a video game. So I was at my friend's house, saw this awesome game, and I just had to have it. My brilliant first idea? I copied the icon from his desktop onto a flash drive. I got home, all excited, double-clicked it, and nothing. Zip. Turns out, all I had copied was the shortcut, which is basically just a signpost that points to where the real program is. Totally useless on my computer. Okay, fine. Back to my friend's place. This time, I was smart. I found the actual game file, the real.exe, and I copied that. I was so sure this was going to work. I get home, I double-click it, and bam, a totally new, super confusing error pops up. Dynamic link library not found. What in the world is that? And that was my crash course in what DLLs are, dynamic link libraries. See, the game was dynamically linked. That .exe file I copied was tiny because it was counting on all these other separate DLL files to handle stuff like graphics and sound. Those files were on my friend's computer, but they weren't on mine. The program was looking for its buddies, and I had left them all behind. That's the dynamic linking trade-off right there, in real life.
So we figured out that a program needs all its connected files, its DLLs, to run. But there's another rule that's even more basic, even more fundamental. The program has to speak the right language for the computer's brain, its CPU architecture. Think of it this way. A program that was built for an ARM processor, like the one in your phone, is basically speaking Spanish. And a program built for an Intel processor, like in a lot of laptops, is speaking Chinese. They use completely different instruction sets, their own unique machine code. You just can't run one on the other because they literally do not understand each other's language. And look, hearing about all this stuff, DLLs, CPU architecture, it can feel like a lot, but you don't have to learn everything about computers at once. The best way to do it is to just be like a magnet. Let yourself get pulled toward the topics that you find cool, whether it's how networks work or how graphics are made. Just follow your curiosity. Okay, let's bring it all together. We've talked about what programs and processes are and how they even get made. Now for the final, super important piece of the puzzle. Where do these things actually live inside your computer? And here it is, nice and simple. Programs live on your disk. Your hard drive, your SSD, that's their permanent home. But processes, the active running ones, they live in your computer's memory, the RAM. RAM is the super fast temporary workshop where all the actual cooking gets done.
So this is the whole journey, the big transformation. It all starts right here, as a static, quiet file just waiting on a disk. And it becomes a living, breathing, dynamic process, actively executing in memory.
And this isn't just some random fact. Getting the difference between a static program on a disk and an active process in memory, that is one of the biggest secrets to understanding how computers really work. Which leaves us with a really interesting question. Your computer isn't just running one process, it's juggling hundreds of them at the same time. How on earth does it manage all that chaos, making sure every single process gets a turn without everything crashing down? Well, that is a secret for another day. Thanks for watching.